telling you a story. So this is a story of intrigue, suspense, and compiler optimization. The best kind of story. So this is a story that happened in 2011 in the Racket community. So what happened is that one of our users set out to write a ray tracer. And we'll call him Neil because Neil was his name. And so Neil wrote quite a nice ray tracer that could render all kinds of materials, different reflections, and generate some pretty pictures. So at some point we decided, the core Racket team, to start using that ray tracer to render icons and logos in the Dr. Racket IDE. Now for all of its nice things, the ray tracer was actually, had a fatal flaw. It was quite slow. Slow enough that at some point it became a bottleneck in the build process of the IDE. So picture this for a second. On the one hand, you have building an entire IDE. And on the other hand, you have rendering a handful of icons. And the icons were winning. So that's how bad the problem was. Now, of course, Neil, being a good programmer, decided to try to solve this problem. And so he did, what is probably your first reflex as well. He took out his trusty profiler and tried to figure out what was happening. And the profiler did as profilers do and told him where the time was being spent in his program. But that didn't really suggest any actionable courses of action on how to solve these bottlenecks. And so eventually, Neil kept searching, and at some point ran out of options and sent a desperate email to the Racket mailing list asking for help. Like, hey, I have this ray tracer, it's too slow, what's going on? And eventually, after hours and hours of poring over the output of disassembly tools and other low-level performance tools, the author of the Racket compiler himself managed to figure out what the problem was. So to cut straight to the end of that story, what happened is that 3 key helper functions deep in the bowels of the ray tracer were not being inlined at all by the compiler. And as Cliff Click reminded us a couple of days ago in his talk, inlining is the mother of all optimizations. If your inliner does a good job, it gives a lot more room to work with to the other optimizations down the road. But on the other hand, if the inliner doesn't do a good job, then you're missing out on a lot of opportunities. So that turned out to be quite a problem. Now, of course, with that diagnosis in hand, the treatment is actually quite simple and obvious. All Neil had to do in this case was to add an inlining pragma that a compiler recognized and automatically inlined the relevant functions. So at this point, the ray tracer was fast, and everybody lived happily ever after, right? Well, I think there's something deeply unsatisfying about this story. So first of all, it took most of a day to actually find the problem and find a solution. So that's quite a long time. But not only that, but it actually required the personal involvement of the author of the compiler, which is definitely not something that every programmer can expect any time. So that's not something that scales. So clearly, there's got to be a better way to deal with these kinds of problems. And a second observation I'd like to make is that while that particular story that I told you happened in the world of Racket, this could have happened anywhere. Anytime you have an optimizing compiler, there will be cases where that compiler will not optimize as much as you would like. And stories like that are probably happening every day around the globe in various languages. And in the case that interests us in particular, these kinds of stories are happening in JavaScript. So now I'll do a slight detour and tell you about how we solved this problem in the Racket world. And that's previous work that I presented at OOPSLA a few years ago. But always keep in the back of your head that we're going to be taking this to JavaScript. So you can't forget about JavaScript. This is ECOOP. So what we did to solve these problems is we built a new kind of performance tool that we called an optimization coach. And this would provide programmers with a button in their IDE that they could click. And seconds later, they would get highlights in their IDE, essentially showing problematic regions. And if they ask for more information, the tool could tell them, hey, look at that there. That function is not being inlined at all. You may want to look into that. Oh, and by the way, if you want to fix it, here's what you can do. So with a tool like that at their disposal, programmers can solve the problems like the ones I just showed you in a fraction of the time without having to resort to any mailing lists or anything. So we saw that this worked pretty well in Racket. Now the question is, can we transpose these ideas to JavaScript? And the answer is yes, and this is what this talk is about. And specifically, this talk is about bringing this notion of optimization coaching to the SpiderMonkey JavaScript engine that's inside the Firefox web browser. Okay, now for the rest of this talk, this is roughly the roadmap we're going to follow. So first, I'll give you a more precise explanation of what optimization coaching is, what it's for, etc. Then I'll give you a little under the hood peek to show you how the coach works. And then finally, I'll show you some experimental results to show you how well the coach actually works. So let's first start by telling you what optimization coaching is. So at its core, optimization coaching is a form of dialogue between compilers and programmers, by which compilers provide feedback to programmers about the performance of their programs, specifically about how well their programs are being optimized. And the most important piece of information that's being carried in this dialogue is what we call optimization near misses. That is, optimizations that did not apply, that the optimizer did not apply to the program, but could have had the program been slightly different in a way that would have made the compiler's job easier. Now, on the left of the slide, we have an example, an excerpt from a report that our JavaScript coach gave on when run on a ray tracer written in JavaScript. I really like ray tracers. And here, what we can see is that on line 432 of this ray tracer, there was an assignment to the isHit property of some object. And the optimizer attempted to inline the code for that assignment, but unfortunately it failed because that assignment would sometimes be a plain assignment and sometimes would need to actually add the property to an object. And this kind of non-uniformity caused the optimization to fail. Now, of course, in addition to providing these near misses, an optimization coach should also provide programmers with recommendations, give them concrete program changes that they can do to resolve these near misses and enable more optimizations. And in the example that we have there, one solution that a coach recommends is to consistently initialize the relevant property inside the constructor so that by the time the object flows to the assignment site, it's always an assignment and never adding a property. And doing this transformation will improve the performance of the ray tracer in this case. Now, one question you may have is, if the coach already knows how to make your program faster, why doesn't it just tell the compiler and have it do it automatically, right? Why do I, as the programmer, have to get involved? Well, the reason for this is simple. Compilers have to be conservative. They have to preserve the semantics of your program as you have written it. You, as the programmer, may be perfectly happy with a very slightly different program that has different semantics, but that for your purposes is perfectly equivalent. But that's a call that only you, the programmer, can make. The compiler cannot do that for you. Now, to make this concrete, imagine that you're writing a program in JavaScript that works with rockets. So in one part of the program, you enter the data for the Saturn V rocket, which is a height of 110 meters, and 3 stages. And elsewhere in the program, you're entering the data for the Ariane 5 rocket, which, as we all know, has 2 stages and a height of 52 meters. Now, in one case, we put the height of the rocket first, and in the other, we put the number of stages first. That may have been intentional, that may have been an accident, but the fact is, had we actually been consistent and put the height first in both cases, or stages first, it doesn't matter, this uniformity would have enabled more compiler optimizations to happen. So one would hope that maybe the optimizer under the hood could just change one definition of Ariane 5 to the other. But unfortunately, that's something that would not preserve the semantics of your program. So here's a little snippet of JavaScript code that can distinguish between these 2 versions of the Ariane 5 rocket. It simply iterates over the properties of an object in order and prints them. So that seemingly simple transformation that may be perfectly innocent in your program is actually out of the reach of a compiler. And so you're stuck with the slow version of accesses to rocket properties. Now, what if instead you had an optimization coach that could tell you, hey, wait a minute, you're not initializing these properties always in the same order, but if you were to do so, then good things may happen. Then you, as the programmer, can decide, was it actually intentional that I put these properties in different orders? If not, then I can just switch it and get more performance out of it. So by having the programmer in the loop, coaches can be more aggressive than compilers. They gain power because recommendations can change semantics. The programmer is always has the right to veto a recommendation that would cause undesirable changes, and we gain power that way. Now, of course, that power comes at a cost. Programmers are human beings. They're not computers, and as such, they have very limited bandwidth. So we need to be very careful when designing an optimization coach to not drown programmers in irrelevant bits of information. So we need to carefully curate the information that we show to the programmer, both in terms of quantity of information, but also in terms of quality. We need to make sure that what we show to programmers is actually actionable and can lead to improvements. Otherwise, programmers will just get tired of the tool and stop using it altogether, and we lose, and we don't want that. Okay, now, why are we doing this for JavaScript? Well, I think this is really a question that has 2 sides. So first, what does JavaScript bring to the coaching research program? So we already know that coaching works in Racket. We've done that for a few years. It's been really successful. But we're scientists here. Does this idea generalize to other settings? And especially in this case, can the idea of coaching generalize to an environment with a JIT compiler? because the parts of Racket that we studied are strictly limited to the ahead-of-time compiler, and JITs introduce complexities. Can a coach deal with that? And similarly, can a coach work with object-oriented languages, with object-oriented optimizations? The portions of Racket that we studied were part of its functional core, and so that's a whole set of different optimizations. Can a coach handle those? And to flip the question around, what does coaching have to bring to JavaScript and JavaScript programmers? Well, for those of you who may have tried, writing fast, performant JavaScript programs is not an easy task. It's very easy to accidentally write something that underperforms and to not even know about it until it's too late. But at the same time, JavaScript performance matters. You may be developing your JavaScript program on a modern machine with gigs and gigs of RAM, but somebody somewhere may be trying to run your website on a Clinton-era cell phone, and you would hope that it would still run at a decent speed for them. And to make matters worse, a lot of JavaScript programmers out there are not experts. Some of them may be web designers that every once in a while have to edit some JavaScript code, but most of their skills are in the design parts of it. And you would hope that they can write decently performant JavaScript code and not make a mess. Or similarly, you may have very experienced programmers that may know all the ins and outs of optimizing, say, Ruby or Java, that every once in a while have to venture from the back end to the front end, but may not have the necessary skills to write performant JavaScript code there. So this is the kind of situation that really calls for tool support, and that's what we're trying to bring. Okay, so now that we have an idea of what we want, let's see how we can get it. So at its core, an optimization coach operates in 4 main phases, and I'll walk you through each of those briefly. So first, we're interested in finding out what's happening in the optimization phase to eventually summarize what happened to the programmer. And because of that, we need to find out what happened during the optimization phase. And we do that in our coach by adding instrumentation code inside the optimizer. So in this case, that means we have instrumentation code inside the IonMonkey JIT compiler within the SpiderMonkey JavaScript engine that records all optimization attempts and whether those were successful, whether they failed, and why. Then step 1.5, we need to get that information out of the engine for further processing. And there's some trickiness there, and the solution we came up with is to smuggle that information through the profiler into the outside world. There's details on the paper. And now that's when the work of the coach really begins. After execution is over, we have this giant pile of raw, low-level optimization information, and we need to whittle that down to something that's consumable and actionable to programmers. And the coach does that via a series of offline steps, the first of which being optimization analysis, which is responsible for curating that list of failures, successes, and all that into something that makes sense to programmers. After that's done, the coach needs to generate recommendations that go alongside these near-miss reports, which it does by a combination of picking textual templates based on the kind of optimization attempted and the reason of failure, and filling them in with information about specific near misses that happened. And then finally, the coach needs to show these near misses and recommendations to programmers so that they can either take action and solve problems or decide against them because that would violate their intended semantics. Now, I'd like to zoom in a little bit into the optimization analysis phase to show you, what kinds of transformations are required to make this information digestible by programmers. So I'll show you specifically 2 techniques that are both there to handle the kinds of complexities that arise in a JIT setting. So the first one we call profiling-based badness. So the idea here is to compute what we call a badness metric that tries to estimate just how much of an impact does a given near miss have on the performance of a program? How much does it hurt? Because not all near misses are created equal. And of course, as the name of the technique says, we're going to be using profiling information to derive that. So to walk you through this transformation, I'll use the following execution as a running example. So this is very simple. Again, we're writing a program that deals with rockets. It has 2 functions. First, we call the launch rocket function, which simply launches the rocket into the atmosphere. And then once that's done, we call the track rocket function, which simply looks at where it is in the sky. So 2 functions, one run after the other. That's what our program is doing. Now, at time step 0, the launch rocket function starts executing and all that. But at time step 3, the engine notices, hey, that function has run for a whole 3 seconds. It's got to be pretty hot. And so the engine decides to compile it, and then continues executing the compiled version of that function, which runs for another 4 seconds, after which execution is over for the launch rocket function, and we switch to the track rocket function, which again runs for 3 seconds. The engine notices it's hot, compiles it, and keeps going with that compiled version. And eventually, at time step 18, the engine decides to recompile the track rocket function. It could be because some of its previous assumptions that it made during the previous compilation were invalidated, or because of a host of other reasons. It doesn't really matter in this case. And the second version of track rocket runs for 2 seconds, and the program execution is over. Okay, so that's what happened during the execution of the program. Now, during each of those compilations, a number of optimizations will have been attempted, some of which may have succeeded, some of which would have failed. And so I'll look at one particular failure for each of those compilations. So when compiling the launch rocket function, there was at some point in the function an access to the stages property. So somebody tried to read the stages property out of a rocket, and the compiler decided to try to generate a polymorphic inline cache to speed up the access, but unfortunately failed to do so because an exotic object may have flowed or may have been taught to flow into that site, and the optimization failed. What exactly is the optimization? What exactly is the failure? Doesn't really matter. What matters is that an optimization was attempted and it failed. Now, during the compilation of the track rocket function, there was an access to the rocket.height property, and the optimizer attempted to compile that to a direct load, so essentially just look up a fixed offset into the layout of an object and just look there. But unfortunately, this failed because there were the property was in different locations in different object layouts, like we saw earlier with the two property orders. So that optimization also failed. And then when we recompiled the track rocket function, that problem was still around, and so we repeated the same failure. Now, as I mentioned, not all of these failures are equally damaging to program performance. All other things being equal, a failure in hot code is going to be more problematic than a failure in cold code. And so to essentially provide this first value for the badness metric, we simply approximate it using the amount of time that a particular compiled version that suffered from a given near miss has been running. So in the case of the near miss affecting the first compilation of launch rocket, that compiled version started running at time step 3 and ran until time step 7, and so we'll give it a badness metric of 4. Then for the first version of track rocket, that version started executing at time step 10 when it got compiled, and executed until time step 18, and therefore has a badness metric of 8. And the second version of track rocket, on the other hand, only ran for 2 seconds, and therefore has a lower badness score. And so what's happening here is that we've identified that the near miss that's in the middle is the one that's most likely to be affecting program performance negatively. And so this is the one that the programmer should really focus on fixing. And so when we rank these near misses later, that one should rise to the top. This is the highest payoff for lowest effort. Okay. Now, second technique, you probably noticed that the two near misses on the right are actually the exact same near miss. And in fact, that probably means that they're both symptoms of the same underlying problem. And that therefore, if the programmer were to fix one of them, then they would likely fix the other at the same time. So if the coach were to show both of those to the programmer at the same time, then they would think, the tool is repeating itself, and we're getting dangerously close to throwing away the tool territory. We don't want to be there at all. So what we can do to increase the information density of what we're showing to programmers is we can merge these two reports into a single one that summarizes what happened in these two cases. And in this case, most of the information stays the same because it was the same kind of failure, but we need to add the badness metrics because we need to essentially reflect the fact that these were two separate failures with each their own contribution to slowdowns. Now, these two techniques I've showed you are only two of many that our coach uses, and there's a discussion of more of them in the paper, and some of them are there to handle the kinds of optimizations and optimization failures that happen in an object-oriented setting, and others are there to handle complexities that arise in a JET setting, and others don't really fit in either category but are useful nonetheless. So more in the paper. Okay, good. Now let's look at some experimental results to see how well this fares. So the first thing that we want out of a coach is we want to make sure that following its recommendations will actually improve performance. That's why we embarked on this whole enterprise in the first place. And so to assess that, we performed the following experiment. So we picked a set of JavaScript programs, we ran the coach on them, which generated some recommendations. Then we followed these recommendations, which involved making some changes to the program. And finally, we measured how much faster these new versions were compared to the previous version. So the numbers on the slide are the result of running the before and after version on SpiderMonkey, so the JavaScript engine inside Firefox. And as you can see, in some cases, we don't get noticeable speedups from these changes. But in some cases, we can get up to almost 20% speedup, which is pretty reasonable. Now, of course, JavaScript is interesting in a way that other languages are not necessarily, in that you may be developing your JavaScript program in your browser of choice with your JavaScript engine of choice. But your users may be running entirely different browsers with entirely different engines. And so it's important to make sure that even by coaching on one particular engine, so trying to make programs more amenable to optimization, in this case in SpiderMonkey, where we'd like to have speedups on other engines as well, or at least not slow everything down. And the good news is that, yes, we can get speedups on other engines as well. So these are the results of performing the same experiment, so simply running the before and after version on the V8 JavaScript engine, which is inside Chrome, and the JavaScript core engine inside Safari. And as you can see, the speedups are not exactly the same, but are roughly similar. And so I think the bottom line here really is that you can get cross-engine speedups even by making code more amenable to optimization in one particular engine. Now, a secondary observation is that, so these are benchmarks from the Octane benchmark suite, which is the same benchmark suite that engine authors use to compare engines across each other. And as you can imagine, engines are tuned to do pretty well on these benchmarks, sorry. And so the fact that we can still find a 20% speed up there, I think is quite nice. Okay, now of course, performance is not the only thing that we want out of a coach. We're also interested in making sure that the changes that we recommend to programmers do not require an undue amount of effort, because otherwise, again, they're going to throw away the tool if they have to do a tremendous amount of work. So to assess that, what we did is we counted the amount of code that needed to be changed in the process of following recommendations in each of the benchmarks. And the results are on the slide, but the really high order bit here is that, so we had to change at most 42 lines of code. That was the maximum we had to change. And the good news is that all of these changes were very simple mechanical changes. Things like search and replace, moving code around, things like that. Nothing that really required tremendous engineering insights, no giant refactorings or re-engineerings. Very, very simple. So I think we can conclude that recommendations, following them is a pretty low effort endeavor, which is exactly what we wanted. Now, of course, there's other things you may want to evaluate about a coach as well. So as, for instance, you may want to evaluate whether recommendations are good, they actually lead to the expected outcome. And we've looked at that in the paper. And we also include discussion of individual recommendations so you can see what kinds of things the coach can recommend and whether those turn out to be useful. So that's all in the paper. Okay, now a few final thoughts before I finish. So first, what I've shown you today lives in a command line prototype that is available from GitHub, and we also have an artifact that you can download. But of course, a command line tool is not the best form factor for web developers. Web developers are used to having all their tools at their fingertips inside their browser in an integrated suite. So a command line tool is not really what they want to use. Now, the good news is that there is ongoing work at Mozilla by Shu-yu, my co-author, and others as part of the DevTools team and JavaScript Engine team to bring a tool that's based on this work to Firefox. And here we have a preliminary screenshot of the current state of their prototype. It's likely to change before it goes to production, but be on the lookout. This kind of tool is coming to Firefox in the near future. Okay, now to summarize what I said today, I think the takeaway is really that this idea of optimization coaching works. It generalizes beyond the racket setting, and especially it generalizes to a JIT setting, and not just ahead of time compilers. And it also works with object-oriented optimizations, and not just the kinds of optimizations you would find in a functional compiler. But I'd like to pop out one level and talk about the broader coaching philosophy of tool building. So what we've done here is we've noticed that compilers are amazing tools. They do all kinds of crazy things, but they're fallible. Sometimes compilers fail. But even in the process of failing, compilers gather tremendous amounts of information that can be, even if they don't necessarily know how to use it properly to optimize. So the coaching approach here is to take this information and liberate it, show it to programmers. Of course, after having taken some effort to sanitize it, prune it, etc., and make it presentable and digestible by programmers. But the idea is to take this information and liberate it. And the hope is that with that information in hand, programmers can solve problems that compilers cannot solve alone, and help the compiler get out of these moats and solve larger problems. Now, we've done that in the context of compiler optimization, but other parts of our toolchain also have this kind of pattern where they hoard all kinds of information that we could potentially use. So runtime systems also gather all kinds of information that we may want to know about. Operating systems, same thing here. So what parts of our toolchain are these information hoarders that we could try to open up and see what we can do with that information? I don't know. Thank you.
So your experiment was with benchmarks, right?
That's right.
Have you tried other like Alexa websites or cool games in JavaScript, things like that?
So that is, I'll be upfront, this is one of the weak parts of our evaluation, the fact that we use mostly benchmark programs. The challenge here is that we need both programs to be good benchmarks, that is, have some easily measurable quantities so we can compare before and after, but they also need to be sure, go ahead. But they also need to be human readable and human editable, because we're not only running benchmarks, we're really running coaching experiments. So we need to make sure that programs can be edited by humans after seeing these recommendations. And so that severely limits the number of available programs that we can use. But the good news is that now that there's a version of the tool that's coming to Firefox, that opens up possibilities for doing large-scale experiments with programs from out on the web. Because one limitation also that I should have mentioned is that the prototype works with command-line JavaScript, which makes things a little bit harder as well. But with a tool inside Firefox, that opens up possibilities, including eventually maybe even user studies with real-life web developers. So I think that the short answer is that this is a weakness of the current work, but there's a lot of things we can do in the future.
Okay, thanks very much.